right, class, I wanted to go over some examples of how to solve problems using a t-score. So, we use t-scores to estimate populations, means, and proportions when our sigma is unknown, okay? We also use S, our standard deviation of the sample, as opposed to the standard deviation of the population. So here's a t-table, okay? The t-table, we're always going to want to use the area in two tails, right? So let's see how to read this. So if I wanted a sample size of 8 and a confidence level of 90%, that means that my area in two tails, right, that would be 0.10, right? That's the area left over if I want to have a 90% confidence interval. This would be 0.9. This would be 0.05, 0.05. That adds up to 10. But I don't just go to 8. 8 is not my degree of freedom. Remember, degrees of freedom equals our sample size minus 1. So I have degrees of freedom of 7. So I go to 7, and I go over to where I have an area in two tails of 0.10. So I would get a t-table value of 1.895. Now, for a sample size of 105 and a confidence level of 99%, the area left over, right, if I have 0.99 here for 99%, the area left over in both tails would be 0.01 total. So I go to sample size. I want to calculate my degrees of freedom, which is 105 minus 1, so 104. But there's no 104 on this table, is there? So I'm going to pick the closest thing, which is 100. I then find where the area in two tails is 0.01, so I look for where these two intersect, and that's going to be at the value 2.626. So I'm going to label that as my t sub alpha over 2, and that sub alpha over 2 is 0.005. And up here in red, I should have labeled that, my t sub alpha over 2, which is t sub 0.05 equals 1.895. So we need to make sure we know how to calculate our t values. So for t sub alpha, we always use the area in two tails, and like I said on the previous slide, degrees of freedom equals n minus 1. Now instead, before we would have a z value out here, now we have our t value. So error equals our t value times our standard deviation over the square root of n, where n is our sample size. So let's go through two short examples. So I have a random sample of the birth weights of 102 babies, has a mean of 3,103 grams with a standard deviation of 696 grams. So what would be the best point estimate for the mean weight of the babies? Remember, a point estimate is just a point. It's not an interval. So we're going to use our mean of 3,103 grams. That's the best point estimate. Now I need to construct a 95% confidence interval, okay? That means that I need to find the t value in two tails when alpha is 0.05. My degrees of freedom is going to be 102 minus 1, which is 101. So I'm going to go to the t table, and I find a t sub alpha 2 of 1.984. I can now calculate my error, which is 1.98. Sorry, let me write out the whole formula for that for us. Oops. Our error is our t sub alpha 2 times our standard deviation over the square root of n. So I get an error of 1.984 times this standard deviation, which is 696 over the square root of 102. And I'm going to get 136.7. So let's round that up to 137. I can now construct my confidence interval. So I'm going to take our sample mean, 3,103 plus 137, and minus 137. I just wrote that a little backwards. So I get a confidence interval between 2,966 grams and 3,240 grams. The only thing that's different is now instead of using a z-score, we're using a t-score. That's all that's changed. So let's try one more example. So let's suppose we have a sample of 28 students' body temperatures, and we found that X bar equals, our sample mean was 98.2 degrees Fahrenheit with a standard deviation of 0.6 degrees Fahrenheit. So what is the best point estimate for the mean body temperature for all healthy humans? Well, we have to go based on our sample. Now, I know typically, really, it's going to be 98.6. That's what we've come up as the best point estimate. But because of our sample, it's going to be 98.2 degrees Fahrenheit. Now I want to construct a 99% confidence interval. That means my alpha is going to be 0.01. That's the area in 2 tails. My degrees of freedom is 28 minus 1, which is 27. So I go to my t table and I find a t value of 2.771. So my error is my t value times the standard deviation over the square root of my sample size. So that gives me 2.771 times 0.6 over the square root of 28, which gives us a 0.3. So I'm going to take 98.2 minus 0.3 is less than our population mean, which is less than 98.2 plus 0.3. So I get a confidence interval of 97.9, which is less than 98.5. Now let's think for a minute. This is a total sidebar. The true population, if I was going to ask you, hey, what's the normal body temperature? You would say it's 98.6 degrees Fahrenheit, right? Like that's what we learned in school. But that isn't even in our confidence interval, okay? What could we do in order to make sure we get 98.6 in this confidence interval? Well, we can't take a bigger confidence interval than 99%, right? That's about as wide of a confidence interval we could get. If we took a 95% confidence interval or a 90% confidence interval, it'd be even smaller, right? So like this is our 99%. This is our 95%, and then 90, that's even tighter, right? And I've got our mean in the middle. One thing we could definitely do to make sure this is the case is this is a tiny sample, right? It's even less than 30, which we typically don't like things to be, but this is normally distributed, okay? So we could increase the sample size in order to make sure that 98.6 was truly in our confidence interval.